Dear student, we are now in the third and final lecture of the topic special functions. And in this class or in this lecture, we will be discussing about the following topics. That is, the outlines of this class are given here. First, we will solve some problems regarding gamma function, and then we will come to another uh, special function which is called error function and denoted by ERF x as it is written here. Then some properties of the error function, and after that complementary error function ERFCX that will be discussed, and then we will expand ERF error function in series, and after that a problem regarding or related to error function. So now come to the first topic of this class, to evaluate some problems. Number one, as we have calculated or evaluated some problems up to serial number 3 in our previous class, that is in lecture number 2 of this series, and now so the problem is has given the serial number 4. Here are this consists of 3 problems, and these there are 3 integral given here, and we have to find out their values. Now come to the first one, which is let I is equal to 0 to infinity e to the power minus 4z square dz. We are here to compute the value of this problem of this integral. And to do this, just write this term, that is 3 to the power minus 4z square, in this fashion. Let us come to here. In which manner we can rewrite this term or this part of this integral. So limit is here as it was previously 0 to infinity, and now e to the power, this can be written as e to the power log 3 to the power minus 4z square, because you know that e to the power log x is equal to x. So 3 to the power minus 4z square can be written as e to the power log 3 to the power minus 4z square, and dz is there. Now this can also be written as e to the power minus 4 log 3 z square into dz, because you know that e to the power x to the power y is equal to e to the power xy. So we have reached, or we come to this expression, that is y is equal to 0 to infinity to minus 4 log 3 z square dz. Now we are substituting 4 log 3 z square as x, and from here, so you can find that root x or x to the power half is equal to root over 4 log 3 into z, and from here you easily find out z is equal to x to the power half by root over 4 log 3, and then dz is equal to d of x of root over 4 log 3, and from here, after differentiation of this term, you will get this is, since this is a constant term, so 1 by 4 log 3, then half will come appear due to this power, then x to the power minus half and dx, that is equal to half root over 1 by root over 4 log 3 x to the minus half dx. Now come to the expression here, this expression, and in this expression, see from this relation that the limit of integration will remain the same. Just look at this, and you can easily understand that the limit will be unaltered. So here 0 to infinity, and this half, first I am writing here, this half is here, and then 1 by 4 log 3, and 2 is taken outside this root square root, so here is 2, then square root log 3, then this term, that is e to the power minus 4 log 3 z square, that is nothing but e to the power minus x, and then x to the power minus half, which comes from this the value of dz. So here is the term, here is the expression that we will get from this expression. Okay, now let us we calculate this value. Now this can be written as, this term can be written as 0 to infinity e to the power minus x to the power half minus 1, because half minus 1 is nothing but minus 1. Okay, then you know from the definition of gamma function that gamma n is equal to 0 to infinity e to the power minus x to the power n minus 1. So in this case n is equal to half. So from this you can obtain this two will give you 4, so 1/4 log 3 gamma half. And you know that gamma, the value of gamma half is root pi. It was calculated in our previous or lecture number 2. So I is equal to, finally we calculated or computed as root pi by 4 log 3. So in calculation of these integrals, I hope that you understand it better that using gamma function, the computation of this type of integration becomes very easier. So here is the beauty of the knowledge of gamma function. Now come to the second one, that is 0 to 1 dx by root 1 minus log x, and say it is 1. And now take or consider or let or substitute minus log x is equal to z. And from here you can easily write x is equal to e to the power minus z. And now from this expression you just convert the limits of integration. That is, when x is equal to 0, you can easily find from here that z will be infinity, and similarly for x is equal to 1, z will be 0. So though there is no difficulty to understand this, just look at this expression. And now from this expression you can write dx is equal to minus e to the power minus z dz. Okay. Now our work or job is to substitute the values of this minus log x and dx into this expression. So if we do that, then I will take the form is equal to minus comes from this term due to this term. So minus is here, and the limit of integration is infinity to 0. Then x is e to the minus then this dx is equal to minus z e to the power minus z dz, that is here, and minus square root of minus log x, that means square root of z. So we get this expression from this expression upon substituting the values of z and dx, minus log x and dx. Okay, then from here, from this term you can write 0 to infinity, because the limit has been changed in this case, so negative sign disappears here. So that is equal to 0 to infinity e to the power minus z, and from here z to the power minus half dz, and you know that this is nothing but gamma half. From the definition of gamma function, that you know that 0 to infinity gamma n is equal to 0 to infinity to the power minus z to the power n minus 1. So this minus half can be written as half minus 1. So in this case n is equal to half. So this will give you actually gamma half. That is nothing but root pi, root over square root of pi. So this integration that is here is equal to square root of pi. Now come to the next one, that is given as I is equal to 0 to, let's say it is I is equal to 0 to 1 x to the power 4, 1 minus x to the power full cube dx. And this can be written very easily, that 0 to 1 and x to the 5 minus 1, and it is x to the power it is 1 minus x to the power 4 minus 1 will be here. It is mistakenly written as 3, but it will be 4 minus 1. You see that 1 minus x to the power 3, that means x 1 minus x to the 4 minus 1 will be here. 1 will be instead of 3. It is written mistake. So you should correct this while you will derive this in your own. So from here, so you can write this is as from the definition of beta function, that beta mn is equal to integration 0 to 1 x to the power m minus 1, and then 1 minus x to the power n minus 1. So m is here 5 and n is here 4. I repeat once again that this 3 will be replaced by 1. This 3 will not come here. Here 1 will come here. It is mistakenly written here. Okay. Now, so this is equal to beta phi 4, and you know that beta, the relation between beta function and gamma function, that beta mn is equal to gamma n by gamma m plus n. So beta phi 4 can be written as beta 5 beta 4 by beta 5 plus 4, and here is and also you know that gamma n is equal to n minus 1 factorial. All of these have been calculated in our previous lectures. So just write gamma 5 as 4 factorial and gamma 4 as 3 factorial and gamma 4 plus 5, that means 9, as 8 factorial. And after computing these, you will get 1 by 280. So the integration is, here it is 0 to 1 x to the power minus x whole cube dx is equal to 1 by 280. Now another problem is here, evaluate with the following integrals using gamma function. So number 1 is 0 to 1 root over log 1 by x dx, and number 2 is 0 to pi by 2 tan theta cube plus tan theta to the power 5 into e to the power minus tan square theta d theta. So now come to the first one, that is let I is equal to 0 to 1 square root log 1 by x dx. So in this case you substitute x is equal to e to the power minus t. So if you do that, then dx will give you minus e to the power minus t dt, and then using this relation you can easily change the limits of this integration as given here. So when x is equal to 0, then t will be infinity, and when x is equal to 1, t will be 0. Just use this relation. Now we have to substitute the value of x and dx in this expression. So I is equal to here limit infinity to 0. So infinity to 0, then square root log 1 by, since x is e to the power minus t, that is done here, and into this is into dx is minus e to the power minus t dt. Okay, then I is equal to just replace this change this limit of integration. So it will be minus of 0 to infinity, and this minus will give you a plus. So 0 to infinity, and from here you see that log 1 by e to the power minus t, that will be log e to the power plus t. Okay, and log e to the power plus t, that means log e to the power plus t means only t, and it is square root of t. So this term will give you square root of t, and when it so that is written here, and then e to the power minus t is here and dt is there. Okay, and now this term e to the power minus t is here, it is written first, and then t to the power half can be written as t to the power 3 by 2 minus 1. See here, if you write it, if this t to the power half can be written in this fashion, and that will give you the identical result. So this is written, the t to the power half is written in this manner, and then dt. And you know from the definition of gamma function, gamma n, that 0 to infinity to the minus t, t to the power n minus 1 dt, that is equal to gamma n. So in this case, then is nothing but 3 by 2. So I is from this relation here, I is equal to gamma 3 by 2. And you know that gamma n can be written as gamma n plus 1 can be written as gamma n. So here 3 by 2 can be written as 1 plus half, and that will give you half of gamma half. And you know that the value of gamma half is root pi, root over bar square root pi. So that is, this will give you square root pi by 2. So this is done here. So 0 to 1 square root log 1 by x dx, that is equal to square root pi by 2. Now come to the second problem. The second problem is 0 to pi by 2 tan theta cube plus tan theta to the power 5 into the power minus tan square theta d theta, and say it is equal to I. Now substitute in this case tan square theta as t. So if you once substitute this, that is dt is equal to tan square theta, then differentiate this, dt will give you tan square theta will first give you 2 tan theta, then the differentiation of tan theta will give you sec square theta, and then d theta, and that is equal to 2 tan theta, and you know that sec square theta is equal to 1 plus tan square theta, and here is d theta. So from here you know that tan square theta is equal to t, that means tan theta is equal to square root of t. So that is done here, 2 square root t, and then from here 1 plus tan square theta, that means 1 plus t, and here is d theta. So d theta from this relation, d theta is equal to dt by 2 square t1 plus t. And here is the limits of integration, the limit of integration in terms of t when theta is when theta is 0, then from this relation theta is 0, then from this relation t will be 0, and when theta is equal to pi by 2, then t will be infinity from this relation, because you know that sine pi by 2, because then in that case sine tan theta can, as tan theta is equal to sine theta pi by 2 by cos theta pi by 2, and cos theta pi by 2 you know 0, so 1 by 0 that means infinity. So that is the these are the limits of integration in terms of t. So now just write here the limits of integration, and substituting all these values, that is for tan square theta is equal to t and d theta in this which has the form as given here. Now just substitute these values. So limit of integration is here 0 to integration infinity, then tan theta cube, that means t cube t to the power 3 by 2. From here you can easily write t to the 3 by 2, and tan theta to the 5 is tan to the power 5 by 2. Then this will give e to the minus t, and this value tt by 2 t to the half 1 plus t. And then from here 0 to infinity, you take t to the 3 by 2 as the common term from these two terms, so t to the 3 by 2 and 1 plus t from here, remaining part here is t to the minus t. Then this term is written here, and then dt. Now just cancel these two terms, and from here it will give you half of this 2 is there, so this will give half 0 to infinity. And from here, since it is t to the power 3 by 2 and t to the half is there, so it will give you t and e to the power minus t from here, and dt. So then you can write this in this manner: 1 by 2 0 to infinity to the minus t, t to the power minus t can be so t to the minus t is written first, and then t can be written as t for t to the 2 minus 1 dt. And from the definition of gamma function, you know that that e to the minus t integration 0 to infinity to the minus t t to the n minus 1 dt is equal to gamma n. So here n is 2, so this will be half gamma 2, and you know that gamma n plus 1 is equal to n gamma n. So 2 can be written as 1 plus 1, gamma 1 plus 1. So that will give you 1 by 2 1 gamma 1. That means half into 1, that means half. So the integration of this integral will give you a value of half. So it is very interesting, and as I said already, that this is the beauty of the knowledge of gamma function, because this to calculate this type of integration in the usual method is very difficult, and it will be time consuming. And using gamma function, you see that the final result we have obtained the final result after few of the steps, and the calculation that has computed in these steps is not very difficult. Now come to another problem that is given here: 0 to 1 dx by root over 1 minus x to the power n, that is equal to here. So remember, this integration has already been completed in our previous lecture, that is in the lecture series 2, in the lecture number 2. That is noted here. See problem 1 under the section evaluation of some integral in lecture number 2 of the series. So I am not here to compute this integral or prove this integral. Just skip this one and go to the next one. The next one is show that 1, 3, 5, etc. it goes to 2n minus 1, that is equal to 2 to the power n by square root 5 gamma n plus half. We have to prove this identity or prove this one. So if n is a positive number, positive integer, then you know that beta mn, that is equal to beta nn, because beta function preserves symmetricity. That means if the integers n and n are interchanged, then the value remains the same. So the value of beta nn and nm are identical, and that is here, and that is equal to, you also know from our first lecture from our first lecture of the series that beta mn can be written as n minus 1 factorial by m into n plus 1, in this way m plus n minus 1. It has been proved in our first lecture. So you have to go to, or you have to go through the first lecture where it has been proved. Now in this case I have just adopted that result. So this is here, and now if we substitute m is equal to half, then from here you can get beta half and n, and you know that from due to the symmetric property of beta function, that is nothing but beta n into half, n and half, and but that will be I am here to use the value of m is equal to half in this expression. Okay, so these two can be written as equal because you know symmetric properties of beta function. So that is in this expression just replace n by half. So here is n minus 1 factorial, then half is here, and from here half plus 1, and from the next very term it will come here but half plus 2, and in this way here in this term half plus n minus 1. Just simplify it. N minus 1 factorial is here, and then half is here, 1 by 2, then 3 by 2, then 5 by 2. In this way you can write this as 1 then plus 2n minus 2 by 2, that is 2n minus 1 by 2, and then the left hand side is that is here, that is equal to, you can write this as n minus 1 factorial is here, and let's see here in all the terms in this series contains 2 in this way you can write well, if you consider all these 2 you can write 2 to the power n, so that 2 to the power n is here. So the 2 to the power is 2 to the power n come here. Okay, so 2 to the power n minus 1 factorial by 1, 3, 5, in this way 2n minus 1, and you also know that, so also know that this is equation 25, write it as equation 25, and you also know that beta mn is equal to gamma m gamma n by gamma n plus n. So here beta half n, that will be gamma half gamma n by gamma half plus n. This is equation number 26. Now from equation number 25 you can write 2 to the power n, this is here, then n minus 1 factorial is here, then this term the denominator is written as it was in equation 25, so that is here, and now that will be equal to from here gamma n, that is this gamma n is here, and you know that the value of gamma half is square root pi. So this is here, and from here gamma n plus half. Now from here this can be written as, you know that gamma n is equal to nothing but gamma n is nothing but n minus 1 factorial. It is also proved in our previous lecture. So gamma n can be written as n minus 1 factorial, then square root over pi, and then here is in the denominator n plus half, gamma n plus half. So this n minus 1 factorial and this n minus 1 factorial cancel each other, and from here therefore you can write 1, 3, 5, 2n minus 1, that will be equal to, from this relation, that will be equal to 2 to the power n by square root pi gamma n plus half. From this relation you can write this. This is equation number 27. And it's so the idea that we had to prove is proved here. Now I am writing some lines from this one, the expression 27. In this expression, that is expression number 20. No, from this you can write the left hand side. First write left hand side 1, 3, 5. In this way 2n minus 1 can be written as 1, 3, 5, that up to 2n minus 1. Then this is the extra term 2, 4, 6, in this way 2n, and so in the denominator this term should be here. So nothing is different here, nothing is very difficult to understand here. So that will, if you combine these whole things with these, then that will give you 1, then 2, then 3, then 5, then 6. In this way 2n minus 1, and the final term is 2n, that is, it is the previous term of this term, and here you see that in all term it will consist of 2. So 2 to the power n here, then 1, 2, 3, in this way up to n. So this will give you actually 2n factorial, and this will give you 2 to the n and n factorial. So hence from equation number 27, from this equation you can write the right hand side, that means gamma n plus half, that is equal to then in that case see here 2 to the power n, and so just compute this from this relation you can easily write gamma n plus 1 is equal to square root pi by 2 to the power n and 135 in this case 2n minus 1, and that from that gamma n plus half is equal to square root pi by 2 to the power n, then 2n factorial by 2 to the power n and 2n factorial. So this equation can be derived from equation number 27. Now come to another problem that we have to prove here, that gamma n and gamma 1 minus n, that is equal to pi cosec n pi. In this case obviously m is an integer which has value 0 less than m less than 1. So it is the condition here. So now to do this we have to recall the beta function that is of integer m and n that can be written in terms of gamma function as beta mn is equal to gamma n and gamma n plus n. So now just substitute or replace this m by 1 minus m in this expression. You will get as beta m 1 minus n. So that will give you that, you know, this is the general relation, and if you use beta mm, so next if you use beta mm, that will give you beta m gamma m, then gamma m by gamma m plus m. So in that relation just you put or substitute m by 1 minus m. So that will give you gamma m, then gamma 1 minus m, then gamma m plus 1 minus m. Or it is better to say that if you replace in this expression this m by this m is unaltered as this, and here if you alter n by 1 minus m, then you also get this. So no problem is there. You can think any of these two ways. So that is equal to gamma m and then gamma 1 minus m, and these will give you this m will cancel and then gamma 1, and you know that gamma 1 is equal to 1. So beta m 1 minus m is equal to gamma m and gamma 1 minus m. This is equation number 28. Now come to the definition of beta function. So you know that the definition from the definition of beta function, that beta mn is equal to 0 to infinity x to the power. This is another alternative definition from 0 to infinity x to the power m minus 1, then 1 plus x to the power this n plus 1. So this can be written as beta m 1 minus m. This is equal to 0 to infinity x to the power m minus 1, and then 1 plus x to the power this 1 plus m, that is m plus 1 minus m. So from it, this is the definition that is given here. So beta m 1 minus m is equal to 0 to infinity x to the power m minus 1 by 1 plus x dx. And you can write these as follows: 0 to 1 x to the power m minus 1 1 plus x dx, plus, because you have you are splitting these limits of integration in two parts. One is 0 to 1 and another is 1 to infinity. So that is 0 to, so from here you can write 0 to 1 this term plus 1 to infinity of this term. Okay. So this is equation number 29. Note it. Now just substitute x is equal to 1 by 1. So from the second in the second integral, so substitute x is equal to 1 by y in the second integral. Then if you do this, then you know from here, or you can obtain from this equation that dx is equal to minus 1 by y dy. And here is the limits of integration. If you use x is equal to y is equal to 1, x is equal to 1, x is equal to 1 from this, then y will be 1. And if you use x is equal to infinity here, then y will be 0. It can be easily understand from this relation. So here the second term 1 to infinity x to the power n minus 1 by 1 plus x dx, that is equal to 1. Here is the limit, so 1 to 0, and then x to the power n minus 1. So x is 1 1 by y, so it can be written as y to the power 1 minus m. Okay, because it will give you 1 by x to the power m minus 1. So if you take in the numerator, then it will give you y to the power 1 minus m. And now this is here 1 plus 1 by y. That is the substitute y x in terms of y in this here. So that will give you 1 by y, and then into minus 1 by y square. Sorry, dx will be 1 by y square dy. So 1 by y square dy. So that you will, after simplification 0 to 1, this due to this negative sign, this limit will change 0 to 1, then y to the power 1 minus m from here, and from here it will be plus 1, that is here, and from here minus 2 is here, and then 1 plus y, because you can compute this as y plus 1 by this y will comes to here plus 1, and dy, that is equal to 0 to 1, and from here y to the power minus m 1 plus y dy. So in generally, for generalization, you can write this expression as 0, that is 1 to infinity x to the minus m minus 1 1 plus x dx. This integral as 0 to 1 x to the minus m 1 plus x dx. For generalization, you just replace the variable y by x. This is the general form. Don't be confused. This is the general form. So now from equation number 29, what was there? 29. That was beta m 1 minus m is equal to these two functions. So first one will be unaltered, and second one can be converted into these limits, that is 0 to 1. So from equation number 19, you can write beta m 1 minus m. That is equal to gamma m and gamma 1 minus m. That was calculated also here. That from here. So this value has taken my m minus m. So that is here. So this is beta m 1 minus m. That is gamma m gamma 1 minus m 0 to 1. If you combine these two, that will give you 0 to 1 x to the minus 1 1 plus x, and it will also 0 to 1 x to the minus 1 by 1 plus x. So that is done here. That is done here. 0 to 1 x to the minus 1 plus x to the power minus m by 1 plus x dx. So that can be written as, this can be written in this manner, in this fashion, x to the minus 1 plus x to the minus m, then 1 minus x by 1 plus x. Just multiply this term with this term, you will find that this will give you this, because x to the first term that you are multiplying this with this. So x to the power, if you multiply these and these, it will give x to the minus m, and these will give you x to the power m, and from here these and these will give you x to the minus m, and these will, but actually just compute this, it will give you nothing but this. So it is not required to prove it, but you can do it. So from here 0 to 1 x to the n minus 1 plus x to the minus m dx, just split this or separate this integral into two parts. That is, this is the first one is, and the second one is 0 to 1 x to the power m minus x to the power minus m by 1 plus x. This is equation 30. Now from the first part, that is the first integral that is written here, is equal to just integrate these two terms. The first term will give you x to the m by m, and from the second one x to the power minus m plus 1, that means 1 minus m by 1 minus m, 0 to 1 the limits are. So using this 1 by m plus 1 by 1 minus m. So the first integral gives you 1 by m plus 1 by 1 minus m. Now come to the second integral, that is 0 to 1 x to the power m plus then plus x to the power 1 minus m by 1 plus x dx. That is equal to 0 to 1, and you can write just first this term has written here, and 1 plus x is 1 plus x to the minus 1 dx. Now you have to expand these in series. So the first term is here, and then this term is converted. You know that the series of 1 plus x to the minus 1 is 1 minus x, then plus x square minus then x cube, and in this way, etc. So on, and dx is there. So then I just multiply this term. So first multiply these two terms with 1, that will give you this, and then these two terms with minus x. So from first one, x minus x to the n plus 1, and from second one, minus x to the 2 minus n. Then multiply this with this term, that will give you this. So these are and so many, so and other, so on. And we are not here to take all these terms plus dot 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 etc. We write here as this, and then dx. So just now integrate all these terms. So from first one is x to the n plus 1 by n plus 1. From these, x to the power 2 minus m, then by 2 minus m, and then from here x to the power n plus 2 by n plus 2, and then x to the 3 minus n by 3 minus n, and so on, 0 to 1. If you use the limit, then this will give you 1 by, if you use the limit 0 to 1, then first from here you will get 1 by m plus 1, and from here 1 by 2 minus n, and from here 1 by m plus 2, from here 1 by 3 minus m. The first term is 1 by m plus 1, the second term is 1 by 2 minus m, the third term is this, and term is this, and so on. And so we can write from equation number 30, that is equation number 30 is here. This is there, this is there, beta m 1 minus m, that is gamma 1 minus m, that is equal to this 1 by m, for then 1 by 1 minus m, and then because the first integral, that is this integral, the first integral give you 1 by n plus 1 by n minus 1. 1 minus n, that is written here. So this is for these two terms comes from the first integral, and then for the second integral 1 by 1 plus n plus 1 by 2 minus m, then minus 1 by n plus 2, then minus 1 by 3 minus 1, and so on. That is equal to pi cosec n pi, and that can be written as pi by sin n pi. So gamma 1 minus m is equal to this. Now whether you can write this as the reason is here. This is, I am directly written here that I have directly written here that this term is equal to pi cosec m pi. Now there is another work here we have to do, is to prove whether this series is equal to this or not. That is done here. Cosec x, right? The series of cosec x, that is equal to k is equal to 0 to infinity minus 1 to the power k, 1 by k pi plus x plus 1 by k plus 1 pi minus x. Now just use different values of k starting from 0 to some higher values in this expression, and you will get k is equal to 0 to infinity minus 1 to the power k, and from here if you write cosec m pi, here x is equal to m pi. So from here you will get 1 by k pi plus n pi plus 1 by k plus 1 pi minus m pi. Just now write different values of k from 0 to some higher values, then you will get, if you use k is equal to 0 from the first term, 1 by see here k is equal to 0 means from here this term will vanish to m pi, 1 by m pi, and from here you will get 1 by pi is from here, and minus m pi is from here. Then if you use k is equal to 1, then you will get from these terms with every term multiplies by pi, and if you take pi as a common term, then you will get this. So this series, so we can now understand why this series can be written as pi cosec m pi. So this identity has been proved. Now another problem is here. Evaluate 0 to 1 x to the power m log x to the power n dx. Evaluate this integral, and to do this you consider that I is equal to this. Now substitute x is equal to minus y, and then log x is equal to minus y, and then 1 by x, just differentiate this 1 by x, dx is equal to minus dy, and from here dx is equal to minus x dy, and here is the conversion of limits of integration using this relation. When x is equal to 0, then y will be infinity, and when x is equal to 1, then y will be 0. So the limit of integration becomes infinity to 0, then x to the power n means x to the power it is m. X to the power n means e to the power minus m. Then log x, log x, and you know from here log x is equal to minus y, so it will be minus y to the power n. This is n is here, and then you see from here that dx is equal to minus x dy, so that is here x dy with a negative sign. So here I just changed this limit of integration due to this here negative sign will become here due to this term dx is minus x dy. So the in this line 0 to infinity, so here I have written as this negative sign will not appear here. Here is the negative sign. This is due to this negative sign. It will transfer to 0 to infinity. Now the first term. Now the first term, that means you see from here. You see from here minus y to the power n. That will give you minus 1 to the power n, then y to the power n. So minus y to the power n is here. There is the into e to the y to the power n. Then e to the minus my is here, and e to the power minus y, because you know that x is equal to the minus 1. So you used here e to the minus y, and dy is where if since the limits of integration has been changed in this case, so this negative sign will not appear here. It is positive sign. In this case, you have to write a negative sign, and in this case it will become positive sign. So this you just consider these two things. Here negative sign, there will be a negative sign, but in this case there will be no negative sign, it will be positive sign. So from here minus 1 to the power n, 0 to infinity, y to the power n, e to the power, from these two terms minus of m plus 1 y dy. So now to compute this integral, just consider m plus 1 y is equal to z once again. So y from here z by m plus 1 up. Once again you have to change the limit of integration, and you can easily find out from this relation that y 0 0 then z 0 0 and y 0 infinity z infinity, and from this relation y dy is equal to dz by m plus 1. Now just substitute these values. So y is equal to minus 1 to the power n from here, from this relation minus 1 to the power n 0 to infinity, and then y to the power n means z to the power n by m plus 1 to the power n, then e to the power minus this term will give you minus z, and dz will give you dy will give you dz by m plus 1. So from after simplification, this is minus 1 to the power n, then m plus 1 to the power, here is n and here is another to the power 1, m plus 1 to the power 1. So that will give you minus n to the power n, minus 1 to the power n, then 1 by m to the n plus 1, 0 to infinity, e to the power minus z, z to the power, you can write these n as z to the power n as n plus 1 minus 1, and then dz. And then from this relation, this integral value is nothing but gamma n plus 1. So this will give you minus 1 to the power n, m plus 1, to the power n plus 1, gamma n plus 1. And now you know that gamma n plus 1 is n gamma n. So you can write this is n gamma n, or also you know that gamma n is equal to n minus 1 factorial. So gamma n plus 1 can be written following this relation, that will give you n factorial. So that n factorial is given here, minus 1 to the power n, m plus 1 to the n plus 1. So this integral has the value of this. Now another problem using gamma function, show that 0 to 1 x to the power n square root 1 minus x square dx is equal to 1 3 5 in this way n minus 1 by 2 4 6 n into root pi by 2, where n is an even integer. So write I is equal to 0 to 1 x to the power n 1 minus x square dx. Now substitute x as sine theta. So dx is equal to cos theta d theta. Here is the limit, change of the limit of integration, that is x when x is equal to 0, from this relation theta will be 0, and when x is equal to 1 theta will be pi by 2. So just substitute these values 0 to pi by 2, and from here x to the power is sine to the power n theta and root over 1 minus sin square theta cos theta d theta. Here is the value of dx. So that will give you, after simplifying, that will give you 0 to pi by 2 sine theta to the power n d theta. And you can write this as in this manner, half is here, so 2 will be there, so 0 to pi by 2 sine 2 into n plus 1 by 2 minus 1. You can write this as this, and then cos 2 into 1 by 2 minus 1, because you can write this as because this will give you 1, and then this is it. And this is nothing but half beta n plus 1 by 2 and half. You know that because you know that 0 to pi by 2, 0 to pi by 2 sine to the power n minus 1 theta cos theta to the power 2n minus 1 d theta is equal to beta n. So in this case, m is equal to 2, n is equal to n plus 1 by 2, and m is equal to n plus 1 by 2, and n is equal to half. So that is written here. And you also know that beta function can be converted. Here is written beta m is equal to beta n by beta n plus n. That is done here. Half beta gamma n plus 1 by 2 gamma half, then gamma n plus 1 by 2 plus half. That will give you 1 by 2 gamma n plus 1 by 2 gamma half by from here you will get n plus 1 plus 1 by 2, that is n by 2 plus 1. That is equal to half. You can write this as gamma n by 2 gamma n minus 1 by 2 plus 1. Just compute, this will give you this result. And this term is here gamma half, and you know that since it is written as in the form of n plus 1 gamma n plus 1, that is can be written as n by 2 gamma n by 2. And then from here half, then you know that gamma n plus 1 is equal to n gamma n. So n minus 1 by 2 will be here, and gamma n minus 2 by 2, and this is here. And from here n by 2 is here, and you can write this term as n by 2 minus 1 plus 1. And from here you get I is equal to half gamma n minus 3 by 2 plus 1 from this term, from this term, from this term, n minus 3 by 2 plus 1, then this gamma half, and then n minus 1 by 2 will this n minus 1 is there, and this 2 is, so n minus 1 by 2 is there. And from here you can write n by 2, and this is from here you can write n gamma n, that is here you can write n by 2 minus 1, then gamma n minus 2 by 2. And similarly, and in this way you can write, if you consider the next term, then that will give you half, then n minus 1 by 2, then this n minus 3 by 2 will be here, and gamma n minus 3 by 2 will be there, and gamma half. And from here n by 2, then n minus, from here you can write n minus 2 by 2, that is there, and gamma n minus 2 by 2. And in this way, if you proceed, continue, then I will give you half, then n minus 1 by 2, n minus 3 by 2. In this way, it goes to 5 by 2, then half into gamma, then half. And final term is gamma half. Okay, final term is gamma half. So it is mistakenly it is here 5 by 2, and it will be 3 by 2. 5 by 2, then it is 3 by 2, then half. And in this reason, so it will confuse in this way. And gamma half is there, this gamma half is there. And in the denominator, n by 2, then n minus 2 by 2. In this way, it will goes to 4 by 2, then 2 by 2, and then gamma 1. Last term will be gamma 1. So in this way, you can write half, 1, 3, 5. In this way, n minus 1, and each term is multiplied by, see here, each term is multiplied by 2 in this series. So that is here 2 to the power n minus 1. You can write this as 2 to the n minus 1 in the, since it will be here half is there, 1 by 2. So each term contains 1 by 2. So that will give you 2 to the power n minus 1. So the 2 to the power n in this series you will have 1 by 2 to the power n, that 2 to the power n minus 2 to the power n minus 1, that 2 to the power n minus 1 is taken in the denominator. And similarly, in from this series, each term contains, this is one term before the last term. This is the one order before the last term. So in this way, you can also write this as 2, 4, 6, etc. and 2 to the power 1 by 2 to the power n minus 1. That is taken here. And then square root pi, because you know that gamma half is equal to root pi, and gamma 1 is equal to 1. That is the term here. So that is, here is the integral, that is equal to 135 n minus 1, and these two will cancel out of 246 n square root pi by 2. So it is put. Now Another problem is here, express 0 to pi by 2 cot theta d theta square root cot theta in terms of gamma function. So here I is equal to 0 to pi by 2 square root cot theta d theta, that can be written as 0 to pi by 2 square root cos theta into sine inverse theta d theta. That is equal to 0 to pi by 2, and from here cos half theta then sine to the minus half theta d theta, and that can be written as half and 2 0 to pi by 2 sine 2 into 1 4 minus 1. That will give actually essentially this, and then cos this one is here, sine 2 into 1 by 4 minus 1. This essentially give you this value, and cos 2 into 3 by 4 minus 1, that will also essentially give you that value theta d theta. So that is equal to, you know, the alternative definition of beta function is that beta mn is equal to this, sine to the power 2n minus 1 theta cos to the 2n minus 1 theta d theta. So if you compare this relation on this relation, you can find that m is equal to 1/4 and n is equal to 3/4. So this expression essentially give you half beta 1/4 3/4. Just calculate this using this because of beta mn, you know that beta mn is equal to gamma n by gamma n plus n. Using this relation you can write this, and finally this, and this is the final result. So 0 to pi by 2 cot square root cot theta is equal to half of gamma 1/4 gamma 3/4. Here is the computation details. Computation is given here. Just to look at it. Now come to our next section, that is here. That is here complementary error function. Here is the error function. Here is the complementary error function has taken into twice. So the next term is the mistakenly it comes here as complementary error function. Okay, we will, since it has been taken mistakenly, one page is not here, so we have to do it in our next class. So this is not the last class of this series. We will discuss about the error function in our next class. So we are here to end this class, because the documents regarding error function for the first page of the error function has not appeared here or comes here. There is technical mistake here, so I am ending this lecture here, and the complementary function, the error function will be discussed in our next class. So